Hi everyone, this is Professor Fernandez, and this is Class Notes B in example in Lesson 3. So in this example, we are asked to apply Theorem 3.11. This is the theorem up here, the existence uniqueness theorem for solds, to the IVP's initial value problems. And really the question is, does the theorem guarantee that a unique solution exists over the indicated interval? Okay, great. So let's tackle the first one of these and see how we can apply this theorem. All right, so to part A, let's look at, first of all, the theorem itself. So the theorem says, consider the sold 3.1. So 3.1, we're going to scroll up here a little bit, is the general form of a sold. So I'm going to scroll up here. That's the standard form of a linear second order ODE. So the theorem basically says, consider that general form with g of t equals 0. So now we're talking about a homogeneous sold. And there are some initial conditions given here. Okay, great. So far we're learning that this is a theorem about homogeneous solds. All right. And then suppose further that P of t and Q of t in the sold are continuous on some interval. Great. So those are some additional conditions. Containing t sub 0, right? So this t sub 0 is the t value of the initial conditions. Okay, then, so here's the conclusion. There exists a unique solution that is defined for all t in there. Okay, great. So we have some sense of all the details and intricacies of the theorem. So now let's apply it down here to this example. Great, so first thing, this is a existence uniqueness theorem for solds, right? Linear second order ODEs. This is why the first class notes had you classify ODEs into solds or not. So we won't do that here, right? Both of these examples are second order linear ODEs, but just make sure that you are aware that this is one thing you should check before you use this theorem. Okay, so to use a theorem, we're going to start basically going down the list. So first of all, are these homogeneous solds? Yes, they are, both of them. Great. Do they come with initial conditions? Yes, they do. Here they are. Great. And now comes the other check. Are the P of t and Q of t functions continuous on the interval that contains the t value of the initial conditions? So there is where things are going to change for both of these examples. So the interval, the t value of the initial condition for both of these is 0. Great. Let's look at the first part of this example. So this is the P of t function, P of t, and this is the Q of t function. So P of t here, t squared, is a polynomial that's defined for all t. It's continuous for all t, I should say. And Q of t equals t, same thing, another polynomial continuous for all t. So in particular, they are continuous for t equals 0. So A satisfies this last condition that we are checking. So indeed, for A, we do know that the theorem is going to guarantee the existence of a unique solution. So does the theorem guarantee for this one? Yes. Okay, now we're going to run through the exact same check for B. This is the P of t function, and you can kind of see what's going to happen here. This is the Q of t function in this case. The problem with this one is that P of t equals 1 over t squared is not continuous at 0, the t value that the initial conditions are given at. So we do not know that this assumption is not satisfied. So this theorem does not guarantee that a unique solution exists. So it may still exist, but we just can't conclude it from this theorem because one of the hypotheses of the theorem, which is this condition on the P of t and Q of t functions being continuous, that hypothesis is not satisfied. So I'm going to say for this one, no. Okay, so that's the end of this class notes.